A space elevator sounds like pure science fiction, a cable reaching from the surface of a world into space, carrying cargo without rockets, climbing silently into orbit. On Earth, it remains impossible with any material we can actually build. But once you leave Earth, the answer changes in surprising ways. To understand why, you have to stop thinking about space elevators as one idea and start thinking about gravity, rotation, and materials. These three factors decide everything. Change the planet, and the entire problem changes with it. On Earth, gravity is strong and unforgiving. Any tether reaching into orbit must support its own weight while being pulled outward by rotation. The required strength-to-weight ratio is so extreme that even our strongest real materials fail long before reaching orbital height. Carbon nanotubes are often mentioned, but outside laboratory samples, they cannot be produced defect-free, long enough or strong enough in bulk. This is why an Earth space elevator remains a physics problem, not an engineering one. The Moon breaks that rule immediately. Lunar gravity is only 1/6 of Earth's. The Moon rotates extremely slowly, taking over 27 days to turn once. That means there is no useful geostationary orbit above the lunar surface. But the Moon does not need one. A lunar space elevator would not be anchored to rotation. Instead, it would stretch towards stable gravitational balance points between Earth and the Moon. These points exist because the gravity of Earth and the Moon partially cancel each other. A tether anchored on the lunar surface and extending through one of these regions can remain under tension without requiring extreme material strength. This single difference changes everything. The forces in a lunar elevator are low enough that existing high-performance fibers could theoretically support it. Not speculative materials, not perfect nanotubes. Materials that already exist, produced industrially today. There is no atmosphere to create wind loading. No storms. No corrosion from oxygen or water. Once deployed, the structure would experience a mechanically quiet environment. The Moon is harsh in many ways, but from a structural perspective, it is forgiving. That does not mean it is easy. Micrometeoroids constantly bombard the lunar environment. A long tether would be exposed over tens of thousands of kilometers. The solution is not making it unbreakable, but making it survivable. Redundancy, segmented strands, and active monitoring would be required. Damage would be expected. Failure would not. If built, the payoff would be enormous. Launching material from the Moon requires far less energy than launching from Earth. A lunar elevator could move equipment, fuel, and raw materials into space continuously. It would turn the Moon into a logistics hub rather than a destination. Mars sits between the Moon and Earth in difficulty, and it is where things become complicated again. Mars has more gravity than the Moon, but far less than Earth. It rotates at almost the same rate as Earth, which means it does have an equivalent to geostationary orbit. A tether anchored at the Martian equator could in principle remain stable using rotation alone. From an orbital mechanics perspective, this is elegant. From a materials perspective, it is brutal. The required strength is lower than Earth's, but still higher than what current industrial fibers can reliably provide at scale. The difference between theoretical strength and manufactured strength matters here. Tiny defects become catastrophic over tens of thousands of kilometers. Mars also has an atmosphere, thin but active. Dust storms on Mars are not gentle. They are planet-scale events that can last for months. A space elevator tether would act like a gigantic vertical sail, exposed to wind loading, dust abrasion, and electrostatic charging. Anchoring it would also be difficult. Martian soil is not solid bedrock. It is loose regolith with uncertain mechanical behavior. Any anchor must handle enormous tension while surviving thermal cycles and ground movement. This is why a Martian space elevator remains theoretical. Nothing in physics forbids it, but the materials, manufacturing, and long-term reliability requirements exceed what we can currently build with confidence. Earth fails for a different reason. Even if Earth had no atmosphere, no storms, and perfect anchors, the material problem alone would stop us. The required strength-to-density ratio simply exceeds what we can produce outside a lab. The tether would fail under its own weight before it ever became useful. This creates a strange hierarchy. On Earth, the idea is constrained by fundamental material limits. On Mars, it is constrained by manufacturing reality. On the Moon, it is constrained mostly by engineering effort and economics. This is why serious space agencies have studied lunar space elevators repeatedly, not as science fiction, but as infrastructure. Not something to impress, but something to reduce cost. The popular image of a space elevator often focuses on height. In reality, the true challenge is not length. It is maintaining tension, stability, and survivability over time. The Moon quietly solves most of those problems by being small, slow, and airless. The lesson here is not that space elevators are impossible, it is that they are planetary specific. Change the environment, and the impossible becomes difficult. Change it again, and difficult becomes feasible. If humanity ever builds its first space elevator, it will almost certainly not be on Earth. It will be on the Moon or Mars. Not because the Mars is friendly, but because physics.